My name is Wally Morgan, and my research is entitled Development of the Embedded Smart Predictive Maintenance System for the lubrication of a plastic injection molding machine. The toggle clamping system is an important part of the injection molding process as it controls the clamping and unclamping of the shaping mold. The toggle must be properly lubricated to avoid machine downtime and friction-induced wear. When lubricant is added to the toggle, the lubricant acts as a barrier separating metal to metal contact. However, as cycle number progresses, this lubricating barrier eventually deteriorates, leading to metal contact. There hence is a challenge in order to determine the optimal time to re-lubricate the toggle in order to maximize the use of lubricant while preventing metal contact. The current industry employs an empirical lubricant life estimation, which is a fixed value as to when to re-lubricate, making it not real-time and often lead to inefficient re-lubrication practices. Our method, on the other hand, uses vibration analysis to monitor the real-time lubricating conditions of the toggle, thereby performing predictive maintenance and efficiently use lubricant. Our experiment was conducted on the CIS 650X injection molding machine, and in our experimental setup, we mounted an accelerometer onto the stationary pin of the toggle clamping unit and a strain gauge across the tie bar of the injection molding machine. Both sensors were connected to a data acquisition system, and data was analyzed on the laptop PC. In our experimental setup, we set the clamping force to 240 kilonewtons and completely lubricated for 40 seconds. The toggle was then allowed to clamp and unclamp repeatedly until a screeching sound was detected by the machine operator, at which lubricant was introduced. We performed a total of 5 different re-lubrication cycles. On the screen shows a profile of a single injection molding cycle with the x-axis representing time, and the blue profile is that of acceleration, while the orange profile is that of strain. From a tribological point of view, we know that clamping and unclamping periods are the poorest lubricating conditions due to the squeeze film phenomenon. For that reason, we focus our analysis on the clamping and unclamping periods. We performed several different analyses. The first of which was the time domain. We extracted a root mean squared health indicator. That approach did not give valuable results. We expanded our study to the frequency domain, where we extracted a frequency health center health indicator. Similarly, that approach did not give valuable results. And then we explored the structural response analysis, where we derived a shock response spectrum health indicator, which shows how single degree of freedom systems of varying natural frequency response to an input excitation. On the results on this screen is divided into two parts, where we have the right side is that of the clamping and the left side is that of the unclamping. What we have here is the x-axis represents increasing cycle numbers, while the y-axis is that of our derived health indicator. What we can notice is whenever the data was analyzed with the frequency domain and the time domain, whenever lubricant was introduced to the toggle, there is no significant change in the patterns of data. However, when analyzed with the shock response approach, we can notice when the toggle is properly lubricated, the amplitude of the health indicator remains fairly low. However, as cycle number progresses, the amplitude increases. Whenever lubricant is added back to the toggle, the amplitude once more falls to its baseline, repeating a bathtub-like behavior. Our results was interesting. However, we needed more experimental data to validate our study, as it was only based on data. So we took our study to the laboratory on a reciprocating wear tester. In our reciprocating wear tester, we had an upper specimen, and we had an accelerometer mounted to the housing and a force transducer also to the housing. Our aim in this analysis was to show that there is a relationship between vibration, shock response health indicator that we derive, and that of the force generated, which is a common tool to measure coefficient of friction. In our experimental setup, we had a copper sample reciprocating over a high carbon steel sample. And then in our analysis, what we did was to set the clamping force to 50 kilonewtons, allowed our slider to reciprocate for 12 hours continuously, and we took the force transducer data along with the derived shock response health indicator from the vibration and correlated it with Pearson's correlation. We performed this test with two different types of lubricants, and the results of this study is shown on the screen. What we can notice is that the x-axis is that of the time of sliding, and the y-axis, the blue profile, is that of our frictional force, while the red profile is that of our shock response health indicator. We notice that for both plots, the Pearson's correlation is very good, suggesting that our derived shock response health indicator is a powerful tool that can be used to monitor coefficient of friction in situations where force transducers cannot be installed on industrial machines. In the final part of our study, we aim to perform a cost down in order to allow our system to be widely deployed into industry. Originally, we used a bulky data acquisition system in there in blue, connected to a piezoelectric accelerometer and a strain gauge and a laptop. This totally cost over $100,000 NT, which is not commercially favorable for industry. For that reason, we aim to develop an embedded system in which we embedded our algorithm onto a single board computer, 16-bit resolution, 70,000 hertz system, collecting acceleration data from a MEMS accelerometer. This total cost around $16,000, around 6 times cost reduction. Our total algorithm consisted of a home page, as shown there, along with a real-time monitoring page where the vibration is logged, and then we also had a lubricating history page. Our algorithm consisted of data being sampled at 10,000 hertz. We then, after we extracted the feature during the unclamping period, and thereafter we performed our shock response health indicator on the data. Finally, what we did, we determined the state using Markov's hidden model to determine whether the lubricating condition is healthy or unhealthy, and we performed data storage and we displayed on an external display as shown on the screen. To finally validate that our system can work with different types of machines, we conducted this study on the 230-ton CLF 230-ton, and we obtained a similar bathtub-like behavior when using our low-cost embedded system. In conclusion, the toggle unclamping phase has the most severe lubricating condition due to the squeeze film phenomenon. We showed that the shock response analysis outperforms time and frequency domain in monitoring lubricant degradation, and we showed that the shock response spectrum is a suitable tool that can be used in replacement with the frictional force for sliding contact system. Finally, we showed that it is possible to use a low-cost embedded system as shown there with a low-cost MEMS accelerometer sampling at 16-bit resolution, 70,000 kilohertz. We're able to cost down more than 6 times cheaper and more compact system. That brings me to the end of my presentation. Thank you very much. So, the vibration of the squeeze film, yes sir. The frequency of the squeeze film I have, it is a transient system. So if I can show the vibration, this is a healthy lubricating condition, and whenever the system becomes unhealthy, it looks like this. So the frequency spectrum is not distinct. However, it is a range, so it's a transient vibration. The resolution, the spectrogram here is healthy, while the spectrogram here is unhealthy, and this is the result of the squeeze film poor lubricating condition. So the frequency ranges about 800, within 500 to 1,000 hertz. The frequency here. The right-hand side is an unhealthy lubricating condition, and the left-hand side is healthy. So if you notice, as time progresses, the toggle is clamped, and when unclamping occurs, it unclamps healthy without any transit. However, as the lubricating condition deteriorates, when unclamping occurs, we have this transient feature, which is a result of the jerk generated due to the squeeze film phenomenon. This is the magnitude of the vibration. So the major contribution, yes sir, is to monitor friction during manufacturing process. And if we're able to monitor friction, we can reduce energy consumption during production, and also we can preserve the health of our machines without damaging it. The relationship between the vibration sensor and the structure. So we mounted our accelerometer on several locations of the injection molding machine. From here, we originally started with several positions. However, what we found out was that the better position is that on the stationary pin, because it doesn't capture the low trembling vibration of the machine. So that's why we ended up selecting the stationary pin due to it doesn't get damaged and doesn't capture the low trembling frequency and only captures the shock generated during unclamping. It captures more information with less vibrational noise due to movement. Yes. Yes, sir. Yes, sir. Slopes. Yes, sir. So the physical meaning as throughout the system is we started the processing from a cold start, and during go to this slide. During the cold start, what happened is we have a shorter operational time whenever the system was cold. These are the cycles before relubrication based on the data distribution. And as the lubricant starts to warm up, we are able to obtain a longer operational period before relubrication was necessary. And then as the temperature, we hypothesize that as the temperature starts to increase, then the operational period once more falls back to a lower point. So the changing in slope is due to a lot of external conditions like operating temperature, operating ambient condition, and types of lubricant. Yes, sir. Okay, thank you very much for your time.